Wasabi, you guys! Welcome to Integration B for Intermediates Part 11. This is where the fun section begins. Kind of. So, in this section, we will be doing advanced forced U-Substitutions. Very advanced forced U-Substitutions. We learned how to do forced U-Substitutions from our beginner training. Now, in this intermediate training, we will be dealing with advanced forced U-Substitutions. These are integrals that you will definitely come across in a very competitive integration bee. And this is super crucial. You must learn how to be very comfortable with advanced force U-sub tricks. And there's a lot. ln of cube. You definitely do not want to do integration by parts with this, because then you'll just be doing it way too many times, and it's just it's annoying. So let u equal ln of x. And then e to the u is equal to x. Then e to the u du is equal to dx. So if you derive e to the u, it's e to the u, obviously. So now we have u cubed e to the u du. This is a lot nicer, right? Now this integration by parts, you can just go straight dive into 3u squared, 6u, 6. E to the u is the same thing, right? So this whole integral is just e to the u cubed, and then you just alternate with the signs, and you just keep on deriving until you reach to 0. Because that's just how polynomials work with exponents. E to the x. So, and we just reach here, yep. And then now you just turn everything into, you just put u into ln of x. E to the u is x. And then now you get ln cubed minus 3ln squared. Don't forget your absolute values, or you have a chance of being eliminated. And that's it. Much faster than just integrating by parts multiple times with ln. Alright? Inverse sine squared. Ugh. Again, you do not want to do integration by parts with this. This is disgusting. So, we would go ahead and let u equal inverse sine of x. Then sine of u is equal to x, and dx will become cosine of u du. Aha. So now we have u squared cosine of u du. So now we do integration by parts. Cosine, sine, negative cosine, negative sine. And that's all you get. Okay, so now this is just u squared sine of u plus 2u cosine of u minus 2 sine of u. Right? And then again, sine of u is x, and then u was inverse sine. So this is equal to x inverse sine of x squared plus 2. So cosine, if you remember from our past video, that cosine inverse sine of x is equal to 1 minus x squared. So this is 2 1 minus x squared, because the cosine of inverse sine here. U is inverse sine of x, and then minus 2 sine of u, that's 2x, plus c. dx over 1 plus square root of x, all of that cubed. Oh god. That is terrifying. Oh god. Oh no. Power substitution? I don't think so. I don't think so. We're gonna get rid of everything. Get rid of it. Get rid of it. Let's see. If I let u, what would be better? U equals this, or u equals this cubed? Well, the thing is, we have nothing for our dx, right? So if you want to do dx, you're going to have to do a cube root, on this one. So most definitely we would not want to do this, right? So I just want to throw that at you so that you don't overcomplicate things. So starting simple, u minus 1 squared is equal to x. Then the derivative is just u minus 1 du equal dx. So now we have 2u minus 1 du, and then we have u cubed. Okay. So now this is just power. This just goes on power rule. 2 over u squared minus 2u cubed. This is equal to 2u squared minus 2. Oh, I'm sorry. That's not 2u squared. That's 1 over u squared. I'm doing this first. And then minus, here is 2 over u. Okay. So now our integral, our answer to this integral would be 1 plus square root of x squared minus 2, 1 plus square root of x plus c. Huh. This looks suspicious. If we let u equal 4x plus 1, we're going to be left off with square root of u and whatever this is, right? But let's get rid of that. Let's get rid of that. Let u equal 4x plus 1. Then u squared minus 1 over 4 is equal to x. Oh, so that's what this is going to be. Don't panic. Don't panic. That's okay. Derive this, you get 2u divided by 4. That's u over 2. Du equal dx. Okay. So then we get u over 2 du, u here, and this big chunk is u squared minus 1 over 4. Okay. So this and this cancels out. We have 4 over 2, it's 2. And the rest is just du u squared minus 1. Now, I'm a lazy person, so I'm going to do negative 2 inverse tangent of u, which is square root of 4x plus 1. And I will just leave my answer like this. Okay? So what do we do with this? We can let u equal square root of x plus 1, but then that's going to leave us with square root of u. And I don't like dealing with exponents with fractions. So fractional exponents is just, it makes me slow when I speed integrate. So let u equal that whole bottom. Then we get u squared minus 1 squared, which equals to x. So the derivative of this is times 2u du equal dx. Okay, that's fine with me. 4u u squared minus 1 du all over u. You see, that's fine with me. Now I don't have to deal with fractional exponents. So now this is just u squared minus 1 du. This is 4u cubed over 3 minus 4u. And so now I get 4/3. U is equal to this cubed, and then minus 4, and then u again. And that is your answer. Alright, we have a cube root of 2x minus 1. Again, if you let u equal 2x minus 1, doing the textbook way, you're gonna deal with fractional exponents. I don't like that. So let u equal the whole thing of cube root of 2x minus 1. U cubed plus 1 over 2 is equal to x. That's fine with me, because now the du is just, what, 3u squared over 2. So now I have So what is my x? X is u cubed plus 1 over 2. And then I have u, and then 3u squared over 2 du. I'm fine with this. This is okay. So now we have 3/4. This is better than fractional exponents. So this and this makes u cubed. So we technically get u6 plus u cubed du. This is easy. u7 over 7 plus u4 over 4. Right? So our answer is just 2x minus 1, 7 over 3 plus 2x minus 1 of 4 over 3. Ooh, this is not a good time to conjugate. You see, I'd rather have this whole bottom as u rather than u minus 1. So I'm going to let u equal the cube root of x plus 1 minus 1. So now I have u plus 1 cubed minus 1, which equals to x. And then the derivative of this is, I'm fine with this. The derivative is easy. That's all this is. Alright, let's do it. Okay. 3u plus 1 squared du. And then this whole bottom is just u. Okay. So we have 3 u squared plus 2u plus 1. All that divided by u. This is technically u plus 2 plus 1 over u. That's all you're doing. So now this equals to u squared over 2 plus 2u plus ln of u. Oops, that's a parentheses. So now our answer is going to be nasty. Cube root of x plus 1 minus 1 squared plus 6, and then u is cube root of x plus 1 minus 1, and then plus 3 ln of u, which is cube root of x plus 1 minus 1 plus c. And this long ass answer is our solution for this integral. Holy radicals. So we got a definite integral here. Again, I would prefer the bottom to be u rather than square root of u, so that I don't have to deal with fractional exponents. So let u square root of 1 plus square root of 1 plus x. Then u square, and then minus 1, squared again, and then minus 1 is equal to x. And then the derivative of this was 2u squared minus 1 times 2u du equal to dx. Okay. First of all, our bounds. Plug in 0, we get 1 square root of 2. Okay, I'm a bit scared, but that's okay. We're growing balls of steel. So, plug in 8, we get 9, square root of 9 is 3, plus 1 is 2. Okay. A lot nicer. It's a lot nicer. Damn, square root of 2. It's okay. That's no biggie. 4u, u squared minus 1 du, all over u. Okay. So that's alright. So this is just power rule. So simple power rule. But then we have the bounds. That's okay. That's okay. 8 over 3. If they give us a nasty integral, we'd give them a nasty answer. Minus 2. And then minus square root of 2. That's 2 root 2 over 3. plus square root of 2. I would just leave my answer like this. That's about it. If you're in like Scranton University, then I'm so sorry that you have to simplify this. But in most integration means you don't have to simplify your answers. You can just leave it like this. Okay, this is kind of their problem for putting a nasty integral. Okay. Holy moly. What do we do with this? Let u equal square root of x plus 1, because there's nothing much you can do. So u square minus 1 is equal to x, 2u du is equal to dx. So now we have 3 to the power of u times 2u du. That's okay. This is just integration by parts. It's just integration by parts. The only thing is you would have to divide by ln of 3. And then ln of square 3. So our answer is 2u ln of 3 minus 2 ln of 3 squared. And don't forget that all of this is being 3 to the power of u. And so now our answer is 3 to the power of square root of x plus 1. 2 square root of x plus 1 over ln of 3 minus 2 ln square 3 plus c. And that is our answer. X to the power of 5 times ln square. I see ln square, so I'm gonna substitute that. Right. E to the u du dx, we already know. We've done it so many times. This is u square. And then x is e to the 5u times e to the u. Don't forget that. Do not forget that. You can easily screw up with that. So this is our du, our x5, our ln square. Okay, so now this is u square 2u, 2, 0. This is e to the 6u, right? And it's going to repeat the same thing, except we have the coefficients now. 36, 6 to the power 3, 216. I'm not a math Olympiad, so I don't know, but that's what I'm guessing. So now this is u square 6 minus u18 technically, and then plus divide that. That's 108. All of this multiplied by e to the 6u. Okay, but don't forget that e to the u is equal to x. So the answer is x to the power of 6 of 1/6 ln square minus 1 over 18 ln of x plus 1 over 8. Sorry, 1 over 108, and then plus c. And that's our answer. Okay, don't freak out. Do not freak out. Do not freak out. Just calm down. Calm down. I am throwing at you for awareness purposes. So if you're wondering what the hell is that big O W letter, so this is a Lambert W function. So this is the inverse function. Actually, let me rephrase this. Oops. So you have a function of x to the e to the x. Then the inverse function of this is the Lambert W function. That's what this is. Okay? It's the inverse of x e to the x. Okay. So what do we do? What do we do with this integral? Huh. Interesting, right? So, what are we going to do with this integral? We're going to let u equal the Lambert W function, just to see where this goes, right? And then the inverse of this, right? This would be u e to the u, because we're taking the inverse. So that's how this works. Very cool, right? Now we have e to the u plus e to the u. I don't know why I write it like that. I should probably write it like this. E to the u plus 1 du dx. So this is the derivative. Now, because we did this product rule, well, first of all, 2e squared, plug in x here, 2e squared, that looks like the form of u equaling 2. Then for e, plug in e, it must be 1. Okay, so that's how you would go about this. For dx, we do e to the u plus 1 du. Okay, and then for x is u e to the u, and then we have 1 plus w. Sorry, 1 plus u, because of this wx. Whoa, look at this. This cancels out and this cancels out. Holy mackerel. This is a nice integral. Look at this. From 1 to 2, it's just du over u. That's all it is. So there was no need to be scared, right? ln of u, you just plug in, ln of 1, that's 0. So this whole thing is equal to ln of 2. That's all that is. So the answer is ln of 2. Alright? You see how amazing that force U-sub that was? Very useful. So now that you know how to do that, try doing that with this. Good luck. It's actually not as bad as you think. I'm not trying to scare you or anything. I'm just giving you confidence. Anyways, so let u equal the Lambert W function, because what else is there, right? We don't have a dx, so we need to do the inverse of this, and that is u e to the u equal to x. Okay? So, if this is hard to see, you can see it like this, and then go like that, right? We know that this is equal to wx. What is our function? You remember that the function for this was x e to the x. So if that was hard for you to see, you can sort of remind yourself like that. So that could be like your emergency backup. So, but that's just memory training or memory purposes. But the derivative of this is e to the u plus 1, because of product rule. Okay? And now we can go ahead. Let's see, e, that makes this 1. Sorry, you're plugging e here, and it's formatted as u equal to 1. Plugging 0, well, we need u to be 0 for that to work. So now we have from 0 to 1, e to the u, and then our dx is e to the u plus 1 du. It works out very nicely. So this is e to the 2u of u plus 1 du. So now it's just integration by parts. U plus 1, e to the power of 2u, negative 1, 0. This keeps going, but we're integrating, so it's a half, 1/4. Okay. So e to the 2u, this is u plus 1 over 2 minus 1/4 from 0 to 1. So this is equal to, if you plug in 1, we get e squared. And then plug in 1, that's 1 minus 1/4, that's 3/4. Minus, plug in 0, this is just 1. plug in 0 here, that's a half. Minus 1/4. So that's, yeah, half minus 1/4, that's 1/4. So our answer is just 3/4. Or I guess I could say, oops, to better simplify this. This is 3e squared minus 1. This is our answer. Alright? We're about to learn a very cool trick that I learned from Norwegians. So this is probably one of my favorite sneaky tricks, the Norwegian substitution. So what is this? What is this type of forced U-sub? Now, just looking at this, right? If you're, I mean, for GMAINs and Math Olympiads, they already know like a pattern to this. But if you're a person like me, looking at this just looks devastating, right? You would faint looking at this and be like, what on earth can you even do with this? This looks non-elementary. This looks, you know, this looks nasty. So, what can you even do? I love this integral so much because once I show you the solution, you can't unsee it. So, I'm about to show you the solution right now. So for here, so the secret to this is you divide everything by to the power of 4x. So you get 6/4 x 1 plus 9/4 x. Okay? And now this is just 3/2 x 1 plus 3/2 2x. What do you notice now? This is just a U-substitution of 3/2 to the power of x. This, I call this the Norwegian substitution. I was just, when I saw this, I was just amazed that oh my god, like I could not unsee this. So, the derivative of this is 3/2 x ln of 3/2. So now the integral is 1 ln of 3/2. Okay, plugging in infinity, that's still infinity. Plugging in 0, that's 1. And then we get du of 1 plus u squared. So now this is just inverse tangent. We get, what? Plug in infinity of inverse tangent, that's pi over 2. Minus inverse tangent of 1, that's pi over 4, which equals to pi over 4. So the answer is pi over 4 ln of 3/2. Okay? You may have seen this integral from a past video, but if not, here it is. We're going to let u equal square root, probably would be the best. Square root of x squared plus x. Will that work? Let's see. Most likely not. Most likely not. All right, let's start with x squared plus x. Right. Then here we don't. So we really need du to be 2x plus 1, right? But we don't have anything here. 2x plus 1 is here, right? But watch this. So I call this the blind substitution. And pretty much you're literally just diving, you're giving x variables, you're giving x variables in a du integral. So here's what that looks like. So we have du and you have 2x squared plus 1 squared in square root of u. Okay, but here, notice that in 2x plus 1 squared, this is 4x squared plus 4x plus 1. This is 4x squared plus x, which is u, plus 1. So you actually have 4u plus 1 square root of u. That's what that is. And now, this is just, I should have just integrated with the square root. But I don't mind doing it again. So this is just 2 dw. And then this is 4w squared plus 1. And now I'm going to go ahead and divide the 4 out. Divide the 4 out. We get w squared plus 1/4. This is equal to a half of 2 inverse tangent of 2w. So our integral is just inverse tangent of 2 times w, which is the square root of x squared plus x plus c. So this integral, we're going to sort of introduce you to British substitution. And that is letting u equal x minus 1, x plus 1. Now, you might think, well, that's obvious because it's, cubed. But for some people, it's like, it's a little sketchy because you have x plus 1 here, and it just looks like this doesn't really help. But mainly, when we do this British substitution like this, British substitution just sort of comes in forms like this. I'll use mn, I guess. Some coefficients like this. But most commonly in integration bees, you'll just come across this only. But the most common ones is mostly because of the du. In the du, when we derive this, it's actually 2 over x plus 1 squared dx. And another is u equals 1 minus 2 over x plus 1. And so with this, you can actually solve for x plus 1. So it'll actually be like, or I guess in most cases we'll leave it like this, right? Because that's what we have here, right? So this 1 over x plus 1 is 1 minus u over 2. And sometimes we can solve for x, and the x itself, the inverse, pretty much, is 1 plus u over 1 minus u, which can also be, the advanced technique for this British substitution. But we're not going to use that, obviously. So we are definitely going to use this, and most likely this, because we don't have a du. So we're going to go ahead and jump right into our British substitution. So plugging in the bounds, right, we get -1 here. Then plugging in 1, we get 0 here. We have u cubed. And then here, let's see, dx, we have 2 over x squared plus 1. So we pretty much have something like this, x plus 1 squared over 2 du, and then we have x plus, I forgot about the x plus 1 at the bottom. There's just x plus 1 at the bottom. When we substitute dx, right, And then, of course, this cancels out. But then we have this x plus 1 left. What do we do with the x plus 1? Well, x plus 1 is this here. So we get u cubed over 2, x plus 1, so it would be 2 over 1 minus u, du. Cool. So now this doesn't look like a partial fractions problem. This is simply a geometric polynomial division. And so now this is equal to, from -1 to 0, this would be like, that's a 1 minus u. So because it's 1 minus u, everything would be 0? Not 0, negative, sorry. So now we have a bunch of, oh, I'm sorry, this flips. U minus 1. And then du. You can go ahead. I'm going to factor in the negative because it's actually kind of bugging me. U squared over 2 plus u, and then ln u minus 1, and then -1 to 0. And so the answer would be ln of 2 minus 5 over 6. Okay, here this looks awkward, right? This looks very awkward. But that square root, I want to deal with something with that square root. So let u equal x e to the x. Then our du is going to equal to x e to the x plus e to the x. I'm just going to factor this. So what I notice is if I divide both sides by u, and u is equal to x e to the x, this cancels out, and I get something like x plus 1 over x, which is 1 plus 1 over x, which is exactly what we have here. So this here is du over u, and here square root of u. Simple integral. This is just 2 square root of x e to the x plus c. Very sneaky. So what do we do here now? I'm going to let u equal this whole thing because honestly this radical looks nasty. And maybe there's some way that we can sort of make the inside a lot nicer. So first off, I'm just going to let u square equal 2 minus x over x minus 1. So pretty much u is equal to this whole thing. But just only focusing on this, is there a nicer way that we can simplify this? And the answer is actually yes. If we do plus 1 minus 1, we get 1 minus 1 over x minus 1. Oh, I'm sorry. No, that's not right. It's the other way. Because this is -2 here. So it should be 1 over x minus 1 minus 1. Okay, so that's our u square. Now it's a lot easier to sort of manipulate whenever we come across something. So it's easier for us to reach, to solve for x, pretty much. Okay, but we don't need that right now. The reason why I put it like this, that minus is kind of bothering me. Minus, there we go, is so that it's easier for us to find du. Because now deriving this, it looks a lot easier. When we derive this function, it looks like a quotient rule. So here, this is just simply negative dx x minus 1 square. Okay? Alright, now we go ahead and put everything in terms of u. if we plug in 1 here, it's going to give us, let's see, that's like infinity, because this just becomes like 1 over 0. So infinity, I'm put it on top, so I'm utilizing this negative here to switch the bounds. And then 2 is 0. Okay. Now plugging everything in, this whole thing is u, and then everything else is pretty much du. So we have 2u. Oh wait, careful. It's not just 2u du. We have this stuff as well. We have this stuff. So what is this? What does this equal to? Well, from here, we have u squared plus 1 equal to 1 over x minus 1. So, if this is our dx, then we are pretty much, so our dx is equal to 2u du, and this whole thing is this squared, so it would be under here, u squared plus 1 squared. So, our integral will look like this. Okay, now this looks ugly. I see a bunch of u squares. So, to put this in nicely, we're just going to trig sub it. Let u equal tan theta. And so that now this could be a lot nicer. So now, this would be, I'm going to put that 2 at the side from 0 to pi over 2, because tangent pi over 2 is infinity. And then tangent square, this becomes tangent square theta, d theta. And then the secant square kind of cancels out with some of this, and we'll be left over with secant square theta. And simplifying this further, this actually equals sine square d theta. And if you remember your beginner training, this is just Wally's product. So this is just a half, and then stop there, times pi over 2 because it's even. This is pi over 4 times 2. So this whole integral is just pi over 2. So that is it for advanced U-Substitutions. Again, it's a lot. It comes in a variety of different ways, so the best way to practice is to sort of rewatch all of these integrals and try it yourself and see if you can recall some tricks and stuff so that you're a lot more aware of these techniques. So that's pretty much it. Thank you guys so much for watching, and I'll see you guys in the next part.